My name is Patrick Huber. I will talk in the next 15 minutes about the project I worked on for about the last 1.5 years, which is called NILM at Industry. So as the name says, we were applying NILM in the industry sector. So these are the questions I'm going to answer you, or hopefully. So I want to present you the project partners. What did we set out to do? So what were the goals? How did we do it? And then actually, did it work? So what are the results? And what still needs to be done? And I will conclude with a very short summary. So I work in the iHomeLab, which is part of the Lucerne University of Applied Sciences and Art. We have basically two groups. One concerns smart. Okay, first of all, I want to stress, sorry, I'm getting confused here. I want to stress the word applied. So we're not the ones that develop the new fastest algorithms, but we rather apply what is developed, or we apply to real problems from the industry. So we developed it a bit further, but we are not the ones that really go very deep in basic research. So we have two groups, smart energy management and ambient assisted living. Smart energy management, where NILM is a big topic, of course, ambient assisted living, which concerns how to support people to live longer independently at their own homes. First glance, you might think that these are quite separate topics, but I mean, the unifying theme is human-building interaction, and we have also quite a few technologies that are shared between the two groups. Our industrial partner was the Swiss SMI called Camille Bauer Metrawatt AG, which is part of an international group, Gossen Metrawatt. They already have power quality measurement devices, so they measure, display, and control power quality. And the basic idea was very simple. They thought, why not have an add-on to this device which can do NILM? Okay. So basic setup, I mean, we have the grid, we have then the device, and a factory, a production site, which has many devices. And we want to be able to have a few of these devices. We want to have the disaggregated energy for these devices. And if you look at the mock-up here, I mean, I put that on a daily basis. So really the goal was not to have the exact load followed, but we rather want to have maybe a daily or even a weekly number, which considerably relaxes the problem, of course. So the measurement device, as it is already designed today, measures voltage and current at 18 kilohertz for 3 phases and neutral. So in total, we have actually 8 channels as possible inputs. So first of all, we had to collect data. That's normal thing. We have a main, we meter the main, and we do some sub-metering. Maybe what's not so normal is the high data rate. We have 18 kilohertz on 8 channels, which amounts to about 500 megabytes per 10 minutes per meter. So we did put that on the cloud. If you know the symbols, this is Google Cloud we worked with. So we have here the raw data, and then in order to be flexible throughout the project, we use the Spark cluster just to calculate feature, to be able to recalculate feature or whatever we wanted to do. Then, of course, we do training and have finally something we can train the algorithm which can be tested. Of course, in the final product, that's not really feasible. I mean, these high data rates. So there, the idea would be that we have the features already pre-calculated on the meter and then put that into the cloud. And I think that's quite clear how it works if in inference mode. Before I'm going to talk about the actual approach that we selected, I want to stress 2 points that we considered throughout the selection that we thought these are important. So the difference between residential and industrial. So in a residential setting, I mean, the set of possible appliances plus minus known. So we heard David. So I think it's possible to transfer to some degree, to train on a data set and then transfer that learned algorithm on other unseen data. I think in the case of in an industrial setting, that's not really feasible, at least if you want to look at that problem in a general way. So the consequence from that thinking is that pre-training on transfer is unrealistic, and we actually, if we want to have a product, we need to be able to train our algorithm in a reasonable amount of time. So what's reasonable? We said, let's go for a week at the beginning to see whether we can select data for a week and then train our algorithm. Then some algorithms that are used in residential case, they assume that we disaggregate plus minus the complete energy that we measure. And when we talked about the project with our partner, he said, okay, we might have just a huge part of the energy that is not disaggregated. So we want to be able just to pick out maybe 2 or 3 appliances and disaggregate this energy. And this restricts, the type of algorithms that we can select for the solution. Exactly. So the actual approach that we have chosen was published 2016 by Mauch and Young, and it's a combination of a deep neural network with a hidden Markov model. So that's what I already talked about. We have one model per appliance. So we have, you can think of this as a denoising approach. You have a very noisy signal. You want to pull out a specific signal. Then I show you here a schematic representation taken from the original publication of the state sequence. And so we have this hidden Markov model as 2 emissions. One is the Gaussian probability density function, which models at the end the signal load. And the aggregate signal is then modeled by the deep neural network. And let's look a bit in more detail how training and inference is working. So during training phase, you actually train the lower part of the hidden Markov model with your load signal, and when you have the trained hidden Markov model, you infer the most likely state sequence, and that's then the input for the second stage of the training, where you have a deep neural network where the input is a window of the aggregate signal, and the output of what you train on are then these states. In the inference mode, the history is basically reversed. So here, you of course, you only have the aggregate. So you run your neural network, you slide the window over your signal, and for each time step, you get then probabilities for the states that your hidden Markov model is in. So if you have this state sequence, then you again, you calculate with you recalculate the most probable state sequence with the hidden Markov model. Sorry, and then you know for each state, you know the most probable load that was, or the most probable power that was used by the appliance. So you will know then the most probable load of your single appliance. Let's look at the results. I will show you results from 2 appliances. Color code on the next slide is always the same. So you have in blue the aggregate signal, and if you compare that with the aggregate signals that we saw so far, it's pretty different. So we have, I think, much more noise in that than in a residential. And if you here look at the peak power, consumed power is 120 kilowatt in this case. This is the first appliance that we look at. It's a Reflow oven. That's a device that is used to solder electronic components to their support. Here we worked with the active power. So we have 4 lines, the 3 phases and neutral that we used as input. We used 7 days of data. And you see here, this is almost 1 day. That looks very similar on all these days. Basically have 1 activation of about 10 hours per day. And the test was performed on 1 day of data. So here in orange, you see the disaggregated, what was the output of the algorithm. of course, we see some problems here, and then also here at the beginning, I mean, there are larger errors, but afterwards it looks quite nicely. And if we zoom in, that looks like this. So we have on top and bottom, we have 2 times 10 minutes of data, and just the second graph is just the data following the first graph. Here we see that's the part where we still have this deviation that I showed you in the large graph. But later on, I think here we have almost a perfect match between what was detected and the ground truth. So second appliance was electronics encapsulation machine. So basically, it's a device where you have your electronics and you protect them by encapsulating them. So you protect from humidity, you have better insulation afterwards. So here the features we used were a bit more. We have with active and reactive power, total harmonic distortion, and we worked here at 5 Hertz, not at like the 50 Hertz we used before. So in total here we have 12 features basically going into a neural network. We trained here on 24 days, out of which 14 had activations. So in total we had 208 activations, and here also the activation were not like 10 hours, but just 1 to 2 minutes duration. So here that device is basically quite the opposite from before. We have much lower power consumption with respect to the overall signal and much smaller activations. Test was done here on 2 days of data, and I mean you already see here also the disaggregated signal. It's not, you cannot see much, but if you zoom in, that's what you see. Actually, I didn't mention that before. We have here 2 scales that we can see both signals a bit better. So that's for the overall for the aggregate signal, and on the right side, that's the scale for the appliance and the disaggregation. So what we observe is basically whenever, or almost always, if there is an actual activation of the appliance, then it's correctly detected. The problem is just that our algorithms has the feeling that there is much more activation than there are actually around. So if we summarize that into numbers, so we have here the 2 appliances and different metrics. So that's for the first one is the normalized absolute disaggregation error. So basically look here at sample basis, and that's the metric we optimize on. So here you see that the reflow oven is about at 40% and the encapsulation machine at 84%. The normalized disaggregation error, that's what, I mean, from the application point of view, that's what is interesting, because, I mean, I said at the beginning that we'll look maybe at daily or even weekly summaries. So here, I mean, reflow oven performs very well with 3% error, and encapsulation machine still not that nice, but okay. If you look from point of view of actual energy, I mean, it looks a bit different. So here it's 2 kilowatt hours for the reflow oven, because of course it's a much higher consumer, and 0.13 kilowatt hours for the encapsulation machine. And I think the results, I mean, you can understand them much better or if you look at the error, which is 94, so the amount of signal, the amount of the aggregate signal which is not part of the appliance is 94% in case of the reflow oven, and here it's even, I mean, the appliance it's 0.2% of the actual signal. So when I saw actually this number, I was still quite impressed to have these in that sense high disaggregation quality. So I had yesterday some discussion about the project. What I always said was, yeah, the money is finished. The project is actually not, because we have many open questions, and I think also very interesting. And I think we should work further on. Let's see how we do that, but that's not the question. So I think the most important question is, what about other appliances? I mean, I showed you 2 appliances, which look promising, but I mean, you cannot base a real product on these results. Second point, I think it would be very interesting for a real application if you can estimate before you actually train an algorithm, you can estimate how well it will perform. That would be a very interesting question also to follow. Then I have here a hidden Markov model together with a deep neural network. So you can imagine that there are quite a number of parameters. And also, if you want to scale such an application, you will have to figure out how either to automatically find an optimal parameter set, or you should have a generic solution which just matches all the cases. And then, I mean, I showed you a solution that we thought of that works in the cloud, but I mean, that is also not something that is acceptable for all industries. So one way to go further is also to investigate how such a system could run directly on the hardware of the measuring system. So let's summarize. So the project was performed together with Gummi Bauer Meteorwatt AG and the iHomeLab. In summary, we can say we had a DNN-HMM approach that yielded promising results. I think we're actually at the beginning, even though the money is at the end. And I personally feel that NILM at industry or in production is a very interesting topic, and I hope to see much more publications in this domain from you guys. And with that, I want to thank you for your attention. I want to thank the organizers for the possibility to speak here, and hope to have some very interesting questions from your side.